Welcome everyone. Welcome to my YouTube channel Zero Association. स्ट्रेंथ ऑफ मटेरियल के सेकंड लेक्चर में हम लोग स्ट्रेस एंड स्ट्रेन कर्व फॉर माइल्ड स्टील स्पेसिमेन के बारे में बात करने वाले हैं, जो बहुत ही इंपॉर्टेंट है मैकेनिक्स के लिए भी, मैकेनिकल के स्टूडेंट्स के लिए भी, और भी बहुत सारे फील्ड्स में. सो स्ट्रेस स्ट्रेन कर्व फॉर द माइल्ड स्टील स्पेसिमेन इज ऑल्सो नोन एज लो कार्बन स्टील, ओके, डक्टाइल स्टील, और FE 250 इन इंजीनियरिंग टर्म्स. ओके, सो ये उसके कुछ नाम हैं. सो वी आर टॉकिंग अबाउट द स्ट्रेस स्ट्रेन कर्व, so drawn between the stress and strain. So the values of the mild steel specimen test on the universal testing machine, and the machine is called universal testing machine because the machine is test all the measurements of shear, tension, compression, flexural, torsion, etc. Okay, so this is a type of the machine that is called universal testing machine. And here we are uh, fix our specimen like this, and this machine pulls in this direction, and then the tension is developed in internal parts of this specimen, and we got the values. So and this, it is done to record the amount of the deformation in the specimen and to reveal the proportional the material. So this is the our universal testing machine. So this machine tries to pull the specimen upper side, and the specimen tries to create the tension inside the specimen material to know the amount of the deformation and to reveal its proportion. Okay, so properties. The first, so this is your like this your stress strain curve. So first draw the curve. So strain in x-axis. Okay, so strain in x-axis and stress in y-axis. Okay, and we know that stress equal to force per unit area, that unit is Newton per mm square or megapascal, and strain has dimensionless quantity but change in dimension upon dimension. So here the specimen changes his length, so I take in delta L upon L. So as we started applying the tension force on the specimen, the strain increase in proportional to the stresses. That is, stress is directly proportional to strain. Okay, up to a point A. This is a point A. Okay, this is the point A. So at up to point A, and the curve showed a linear variation, and the zone is known as linear elastic zone. Linear variation, and this is known as the linear elastic zone. Why this is called the linear elastic zone? Because this region valid for the Hooke's law. And what is Hooke's law? Hooke's law is stress is directly proportional to strain, which contains, so stress is directly proportional to strain. So and then after, which includes the constant proportionality E. So we can say that E equal to E, which is equal to stress divided by strain. Okay, and therefore can be said that as the slope of the linear curve, and this E is known as the modulus of elasticity. Since the stress is proportional to the strain up to point A, this point A is called as proportionality limit. So here I just write this. A is known as proportionality limit. Then on further application of a stress, our material reaches to elastic limit and we name it as point D. There will be some point B. Okay. Up to this point, material is elastic and this region is non-linear elastic region. Okay. AB is non-linear elastic region. And the path A to B is slightly curved, therefore Hooke's law is not valid to this region. And in actual engineering graph, like in real graph, this point B is very near to point A. So O, this point is O, OA is equal to OB approximately for mild steel. Okay, but in other, OA is less than OB. Okay, so in actual engineering graph, like the real graph, this point B is very near to point A for mild steel, but in other material, B is kind far from A. So just demonstrate point A and B. I have drawn point B far from A, but actual condition, they are very near. Okay. Then all right, on the application of further more loads, the stress value increase and this graph reaches to a point C. This is the point C. Okay, C. And this point C is called upper yield point. Upper yield point. And after this point, the resistance of the material suddenly drops down and the material become unstable, and this depends on the shape and size of the specimen. Since the internal resistance of the material drops down up to a certain limit, we name as point D. So this is our point D. Okay. So this depends on the uh, and it called as the lower yield point. So I just write here point C is upper yield point and D is lower yield point. Clear? And this lower limit point, and it is preferred for the designing purpose. This point D is preferred for the designing purpose. The stress at this value is taken as design stress for the limit state method, working stress method, and ultimate load method and plastic theory. And the point and this point is known as the actual yield point of our mild steel specimen. Okay, this point D. After this point D, on a very small increase of the load, the deformation are very large as compared to the load applied, which means that the strain value are very large as compared to the stress applied. So which means that on the relative small increase of the stress, it shows a very large value of the strain, and this reason is indicates the permanent deformation on our mild steel. A specimen, and this region is called perfectly plastic region. This region is called perfectly plastic region, and it continues up to point E. This is point. So on further application of loads on this specimen, the curve from E reaches from for a point F, and which is known as the ultimate stress point. So then after ultimate stress point, we are just because this point shows the maximum stress that our specimen can bear during its service life, and in this region between E to F the strain increases with faster rate, and our specimen undergoes changes in atomic and crystalline structure, resulting in increased resistance for further deformation. That is why this region is called strain hardening region. Okay, this region is called strain hardening region, and it is not used for the designing purpose. After this ultimate stress point, on further application of load, the area of cross section drastically decrease and a neck kind of shape start producing in our specimen. Like this is like a neck kind of. Then and our further application of load, the diameter start decreasing and resulting the breaking of our specimen, and the point at which the specimen breaks is called the fracture point or brittle point. On the corresponding stress is called the breaking stress, and the corresponding strain is called the fractural strain, and the region between F to G is called as necking region. So here after D, that is F is ultimate stress point, and G is necking region. Corresponding stress is called the, and the corresponding strain is called the flexural strain, and the region between F to G is called the necking region. And one of the writer is mentioned it that from point F to G is called the strain softening zone, but I am not sure about it. You can cross check it is in your book, but in this neck which I am strain. Okay, so this is called the elastic, and the upper yield point at point C is normally found at the 0.2% or 0.002. Okay, so this was the pretty much about the stress strain curve. There are few more types of stress strain curve I will show you in next part of this videos, and if you found this videos helpful, please hit the like button and really motivates me to create more videos for you. So then and then also you tell me comments below. You don't forget to subscribe to my channel because more videos like this are coming for you. So thank you. Goodbye, take care.